So I think yesterday I mentioned something about differential evolution. So today we will look a little more details about differential evolution. So these are the things I am thinking of covering. Some of the things already covered, I think. The introduction, some of the points I have looked at yesterday, so I will skip them today. And then future of real parameter optimization, how I foresee things evolving, developing from here. That's what I would like to mention there. And then the differential evolution, as I mentioned to you yesterday, there are many problem scenarios like constraint, multi-objective, dynamic, expensive, large scale. There are so many different cases. And differential evolution has been developed for all these cases. But I am going to look at only the bound constraint single objective today first. And then later, if you have time, I will say briefly about constraint handling. I didn't see much about constraint handling in this workshop, so I thought maybe I had few slides on constraint handling. So if you are solving real world problems, many of them may have some constraints. So how to handle them with evolutionary algorithms. So these ideas that you see here, they can be integrated with your other swarm evolutionary algorithms. So if you have other algorithms, you can integrate them as well with these ideas. So for differential evolution, you can look at this particular survey paper published about 2 years ago. I showed this slide yesterday also, some recent conferences to think about computational intelligence conference in Bangalore, and then this is the multi-objective one. And then if you are interested in neural networks, classification, regression, you can look at these also. And Casey has already mentioned about this. I showed you yesterday as well. So we move on to the next one. And by the way, this particular journal is going to have some special issues. One of them is differential evolution. So if you have some papers, you can submit. And then another one is coming up is multi-objective evolutionary algorithm as well. So there will be some special issues on this. So the introduction part, I think I have covered this. I have shown you these slides and we discussed them yesterday. So I will just skip these things. We talked about them anyway yesterday. So this one also I showed you just one slide on differential evolution yesterday. So we start from here anyway. So as you can see here, it was introduced in 1995, and in the next year at the Evolutionary Computation Conference, it performed well in a competition. And there were some studies comparing differential evolution with GA, PSO, and so on for solving real variable optimization problems. And almost always the D is there at the top. And this one also I mentioned. I have been organizing competitions at the Congress on evolutionary computation. Differential evolution is almost always at the top anyway for these competitions as well. So these statements are true for the basic differential evolution, but nowadays the improved versions are very complicated anyway. So they have lots of variations and enhancements, so they are not straightforward. So differential evolution is basically an evolutionary algorithm. So it follows similar steps as other evolutionary algorithms. So you have a population initialization, mutation, crossover, selection. There's a little difference here compared to genetic algorithm, for example. Genetic algorithm will do crossover first and then mutation. Differential evolution is doing slightly differently. Mutation first followed by crossover. Then the selection. The selection is also slightly different in differential evolution. So I will highlight those things. So we are going to look at only real valued problems. That means the decision variables are all real variables. So real parameter optimization. And we also assume that every decision variable has low and lower and upper bounds. So in this case, we are looking at d-dimensional decision variables. So there are capital D number of decision variables, and each one has its lower bound and upper bound. So these evolutionary algorithms, all of them have population. So you initialize a population with NP size. So in differential evolution, the population size is specified as NP, and then you have a capital D number of decision variables, and all of them are real valued ones. Okay. So the population size selection is not very easy. Adaptation is very difficult for population size parameter. Initially, people were working with rules something like 5 times the dimensionality of the problem or 10 times dimensionality of the problem. That was the rule used initially. But later on, people looked at 1000 decision variable optimization problems. That means you have 1000 decision variables, and they try to solve them. They found out that you don't have to scale the population size by 5 times or 10 times. Even a population size of 200 or 300 was able to generate good results. So the population size doesn't have to scale like this. So this is what people found out with 1000 dimensional problems. So the details are available here. I think this one was done about 5-10 years ago now. So this is for the population size. So once you decide on the population size, then you have to initialize the values. The initialization has been done usually by randomization. So every point in the 2-dimensional matrix, you have a 2-dimensional matrix when you look at the population, capital D number of columns and NP number of rows. You have a 2-dimensional matrix. Every element in the matrix is initialized randomly like this. So you generate random number every time, and then the initialization is between the min and max values for each decision variable. So the next step, so once you complete the initialization, by the way, as soon as you initialize the population, you can also do fitness evaluation as well. Fitness evaluation can be done as well. And then the next operation you have to do is mutation. So you generate the initial population, and then you do the fitness evaluation for the initial population. And then the next step is mutation. So to perform the mutation for each vector, that means for each member in the population, for every member in the population, you usually select 3 other solutions from the population randomly. So these 3 members are selected randomly. So they have nothing to do with the particular member that you are going to evolve. So these 3 members are coming pretty much randomly. This is basically one of the mutation equations. So when you talk about mutation, this is one of the mutation equation, and this is the one most commonly used with differential evolution. So I is basically the index for the population member. So the index I, this index I will run from 1 to NP. So your population size is NP. So the index I is going to run from 1 to NP. So if you look at this R1, R2, R3, these are 3 different solution members coming from the population. So the R1, R2, R3, they are different from ith member. and then randomly selected from the remaining population. Okay. So, your total population size is NP. From the NP population size, you exclude the ith member. After excluding the ith member, you select 3 members randomly. So, this is one mutation equation. So, the first one is known as the base vector, and then you make use of the other 2 randomly selected members to form this difference. So, this may be the reason that you call this method as differential evolution, because you make use of these differences here. So, this f is a scale factor. Initially, it was a constant, but nowadays people do adaptation on them. So, you have adaptive methods to tune the scale factor parameter. And differential evolution has an advantage compared to, for example, evolution strategy or evolutionary programming. So, from yesterday's slides, you may remember that sometimes we talk about Levy mutation, Gaussian mutation, and all those things. So, when we talk about Gaussian mutation, you have to specify the sigma value. The mutation step size parameter you have to specify. In differential evolution, you don't have to tune the step size parameter. Instead, this difference vector will do that job. And in addition to this difference vector, you can have a scale factor. This scale factor is a lot easier to tune than the standard deviation in the Gaussian. So, the advantage of this difference vector, how you can visualize the advantage of this difference vector? You imagine initially you have a search space and you are randomly initializing the members all over the search space. So, in the initial stages, the population members may be well separated. So, when the population members are well separated, the difference vector will have reasonably large magnitude, because the population is well separated. So, when the evolutionary algorithm evolves over generations, the population members usually tend to move to a good solution, towards a good region. So, when the members move towards a good region, they become closer to each other. So, when they become closer to each other, the magnitude of the difference vector will naturally become smaller. So, the differential evolution is naturally altering the search behavior from exploration to exploitation as the population evolves. It is doing it naturally by this difference operation here. Okay. So, this is what we call this self-referential mutation. So, the population refers to itself to find out the magnitude of the difference vector. So, the magnitude of the difference vector is basically determined by the population itself. So, that is why we say self-referential mutation. That means you don't need to specify the sigma value or something like that, standard deviation or something like that, you don't have to specify explicitly. So, specifying f is a lot more easier than specifying the sigma value in the Gaussian mutation or Levy mutation or something like that. So, once you complete the mutation, you have to perform the crossover operation. The most commonly used crossover operation is binomial, or this is also known as uniform crossover in genetic algorithm. So, if you are familiar with genetic algorithms, it is basically the uniform crossover. So, to perform the crossover operation, you have to have a crossover rate, and the crossover operation is done between the ith population member and the mutant vector that you generated in the previous slide. Are you able to visualize how these things are happening? Maybe I just give you a little sketch here. So, you have your population like this, then you are going to do the mutation for the ith member. So, you have the ith member here. For this, you are going to perform the mutation. So by doing this operation here, you come up with your mutant vector. So the Vig you obtained. So when you obtain Vig, the ith member doesn't participate in any of this. If you look at the right side of this equation, the ith member doesn't come in. So all these are randomly generated, XR1, XR2, XR3. These may be somewhere over here. R1 may be somewhere here, R2 may be somewhere there, R3 is somewhere there. Okay? So they are coming from different places in the population. So when you want to do the crossover, you would be doing the crossover with this ith member and the mutation vector you obtained in the previous slide. So that is where you are going to do the crossover. And here you have 1 to capital D number of decision variables. Is that okay? So that many decision variables. And then you are going to specify a crossover rate. In the early versions, this particular value is given like 0.8, 0.9 or 0.5 fixed value assigned usually, but in recent time people do adaptation here as well. So the CR value can be adapted as well. So for every decision variable, you generate a random number, random value. If the generated random value is smaller than CR, CR is usually 0 to 1 anyway, the range is 0 to 1. If the random value is smaller than crossover rate, you get the element, get the decision variable from this mutant vector. So the mutant vector is also 1 to D dimensional vector. Okay. So otherwise, the element is taken from the parent. So you take individual elements either from the mutant vector or from the parent, depending on the CR. So okay, so that will give you your offspring. So U is the offspring. So once you do the crossover between the mutant vector and the parent, you will get the offspring vector. So now you have an offspring vector and you have the parent vector. The competition is going to be between the parent and the offspring. So the mutant vector is done with. We are not going to look at the mutant vector now. So the selection. So the competition is basically between the offspring vector. Offspring vector, this one is obtained by performing the crossover between the mutant vector and the parent vector. So you do the crossover between these two to get the offspring. Now the competition is between the parent and the offspring. So if the objective value of the offspring is smaller or equal, you will select the offspring. If the objective value of offspring is higher, then you keep the parent. So when we use this smaller and higher, we are looking at minimization problem. So your objective is to minimize. Okay, so when the offspring beta has smaller objective value, we take the offspring. So in differential evolution, the competition is done between the parent and offspring. So we keep either offspring or the parent in the population. We don't keep both of them, and you can see why we don't want to keep both of them, because the offspring can have some dimension. If you look at the offspring can have some dimensions coming from the parent. Say these dimensions, they may be coming from the parent. Because we are doing the crossover. When you do the crossover, some elements from the parent may be copied into the offspring. So can you see the problem if you allow the offspring and parent, both of them to be into the to go into the next generation population. What will be the problem if you allow the parent and offspring to go into the next generation population? But looking at this one, looking at this particular elements that you are copying. So you are copying some elements from the parent into the offspring. So if you allow the offspring and the parent to exist in the next generation population, what will be the problem? You have to look at the name of the method. Name of the method is differential evolution. So in the differential evolution, you are taking difference between two vectors. If you allow the same values to appear in the parent and the offspring, and if you take the difference between these two, what will happen in the red area? The red area will become 0. So the differential evolution won't move. So if you allow this to happen many times, then the differential evolution will collapse. So that is why they say either parent or offspring, only one can survive. So by using that rule, you make sure that every number in the matrix, every number in this matrix will be different in the early stages. They will become similar only at the convergence. At the end of the search only they will become similar. Otherwise they are all different. So that is why they say you allow only one of them. So that is the reason that we allow only one of them and we do the competition between parent and offspring. By the way, there is another crossover method, exponential or 2-point crossover, but this method is not commonly used because this method has a little bit of shortcoming. Like this method works well if the neighboring decision variables are linked together. Only with one condition this crossover works okay. Otherwise it doesn't work. So because of that, this particular crossover method is not commonly used. So you can usually ignore it. It is very rare to have the linkages between the neighboring decision variables. Linkage means that the first element is connected with second one is connected with third one, and things like that. The decision variables are linked together in a sequential way. So that kind of situation you won't see in real life. So we looked at only one mutation equation earlier. So we looked at only one mutation equation. As you can imagine, there are many mutation equations in differential evolution. So there are so many of them. And this is not the full list. There are many more as well. So you can look at the literature. People are developing different mutation equations. So this one I didn't cover. So by looking at this real valued optimization problems, I feel that the population topologies are very useful. I think the population topology was mentioned by some others also. I forgot. Maybe yesterday it was mentioned, maybe, I think, the topologies. The neighborhood relationships and all those things were mentioned yesterday in one of the talks as well. So initially, the evolutionary algorithm used only a single population. That means when you use a single population like this, we allow all these members to interact. That means you can do the mutation taking any one of them randomly. There is no restriction. So you can pick any 2 or 3 members and perform the mutation operation and all those things. But when you introduce the topology, we try to restrict which members can interact with which members to generate offsprings. Why is this useful? If you have subpopulations, that means if you divide up the whole population into small groups and subpopulation, you have a benefit of delaying convergence. That means you may be able to escape from premature local convergence by doing these topologies. So when you initialize the population, when you initialize the members randomly, there may be one solution which is very good initially. If you allow this good member in the initial population to influence all others, it has a potential to attract others near it. But this initial good solution can be far away from the global solution because you randomly initialize all of them. So, but if you introduce population topologies, that means members that are located near each other can interact with each other but cannot influence the members far away. So, initial bad solution located at one particular place may not influence others located far away from the initial best solution. So, by introducing topologies, you are restricting the interaction within local neighborhoods. So, when you restrict interaction within local neighborhoods, the exploration will happen in a localized manner at different places. And then you can have possibly better solutions. So, topologies are certainly going to be useful for evolutionary algorithms in the case of real parameter, real variable optimization. So, using Euclidean distances, I did some work with PSO because PSO has the problem. Premature convergence problem is very severe for PSO. So, I did Euclidean distance based neighborhood in 99. So, this one is well cited because it is one of the earliest PSO papers as well. So, and this one uses Euclidean distance neighborhood. After this one, we did additional work on Euclidean distance based neighborhood. So, you can see them from my home page as well. Another one that I am thinking of is that ensemble methods. If you have several operators to perform one particular task, like if you have several mutation operators, you may be able to use them all together as an ensemble, and then you can try to learn which one is going to be useful for solving this problem. The learning method I will explain little later. So, ensemble strategies can be used when you have several choices for one particular operator. Another one is adaptation. I mentioned it yesterday also with genetic algorithms. When you have different crossover operators, different mutation, different selection operators, you can have adaptations with ensembles. So, you can put the ensembles with adaptation as well. Adaptations are usually done in two different ways, either self-adaptation or separate adaptation. In the self-adaptation, with the solution string, you can attach the operators, mutation operator, crossover operator, their parameter values, you can attach them and make the candidate solution longer. But what you are doing is you are going to evolve these operators as well. The operators will also evolve through the generations. That is known as the self-adaptation, but then you have something called separate adaptation based on performance. So, usually this separate adaptation is more effective. That means for every operator, every parameter value, you can try to identify how many times this operator is generating better solution. You use one particular mutation equation and then see how many times this mutation equation is generating improved solution. If a particular mutation operator is generating improved solutions more frequently, then you want to use it more frequently later on as well. So, that is more effective. Then this is basically called performance feedback based adaptation. You look at the performance in the recent past and then make use of that information to select operators going forward. So, the second approach is more useful and it is more frequently used. So, nowadays people don't frequently use self-adaptation with this solution string. Adding the operators with the solution string is rarely used nowadays. So, with the adaptation and the population topologies, we have some work. So, one of them is two populations with heterogeneous ensemble and topologies. So, we developed two population approach to illustrate the topologies and adaptation. So, what we did was we had two subpopulations and we developed one subpopulation for exploration, another subpopulation for exploitation. So, you have two subpopulations. One is specifically doing exploration, other one is doing exploitation. You can select the operators and parameters in such a way to increase exploration in one subpopulation, and in another subpopulation we select operators and parameters to increase the exploitation. So how the topology is coming in here, heterogeneous topology. What we did was, with the topology, we allowed the exploitation group to see the whole population. So the exploitation group can see the whole population, but the exploration group will not see the exploitation group. So what is the advantage? If the exploration population finds a good solution, the exploitation group can make use of it to do exploitation. On the other hand, if the exploitation group converges, exploration group will not see that. So the premature convergence in the exploitation group will not affect the exploration group. So we did this heterogeneous population topology and demonstrated it performs better than a single population topology because of the heterogeneous information exchange. Information goes only one way, not the other way. So the and also we showed the population diversity. So when we look at the population diversity, we could see the exploitation population converges to almost zero diversity, all of them going to one point, but the exploration population still can remain diverse. So we were able to show that because the information exchange is only one way. So we have some papers based on that. So this is for differential evolution, and this is for PSO, and this is for differential evolution. So we have done this with a few cases. And they also, in the second work, comes with distance-based, Euclidean distance-based neighborhood as well. So the second one is coming with Euclidean distance-based neighborhood as well. And another research direction that is promising is that population size reduction. You cannot adapt the population size, but researchers recently show that the population size reduction is effective for single objective numerical optimization. That means you start with a very large population, and as the generation goes on, you reduce the population size. So the population size is becoming smaller, and you can justify it as well. In the initial stages, you are going to do exploration. In the early stages, you are going to do exploration over the whole search space. So to do the exploration over the whole search space, you need bigger population. And as the evolution goes on, you change from exploration to exploitation. To do the exploitation of good regions, you don't need large population. So you reduce the population size and the performance will become better within the given computational budget. So these are the things that you can look at, whichever evolutionary or swarm algorithm you are using. You can try to integrate this adaptation, population size reduction, ensembles. You can put all of these when you develop a new algorithm. So we will look at a few differential evolution variants for single objective optimization first. Just 2 or 3 I will look at, and then I will say briefly about constraint handling as well. So this is one of the work we published, self-adaptive differential evolution. The first version was published in a conference in 2005, and this is the journal version. This version was popular because this was the first paper to explain how you can select between mutation operations. So when you have multiple mutation operations, before this work, researchers have to do extensive trial and error search to pick one of them. Out of those 5-6 mutation operators, you do lots of simulations and then say, for this problem, this mutation operator is very good. So instead of doing that, what we did was we put 3 or 4 mutation operators together as an ensemble like, and then we did the adaptation. So how did we do this adaptation? when you initialize the population, you have your initial population and you have about 3 or 4 mutation operators. You have these mutation operators. We take one of the mutation operator with equal probability immediately after initialization. So at the start, all mutation operators have equal probability. Then you run for few generations, like 10 or 15 generations, you evolve the population. So over these 10, 15 generations, you record mutation operator 1 we used 100 times. It gave improved solution 50 times. So success rate is 50% like. Then the mutation operator 2 we used 100 times, it improved 20 times. So the success rate is 20%. So for each mutation operator, you can have the success rate over the previous 20 or 30 generation. So once you have the success rate, going forward, your selection can be now proportional to the success rate. So if a mutation operator is frequently successful, in the future generations, you can use it more frequently to generate better solutions. So that is the adaptation method we introduced here. And that adaptation is for the mutation operator. And for the parameter values, we used a normal distribution, like the crossover rate. For some problems, small crossover rate is very useful. For some problems, very large crossover rate is needed. So the crossover rate is also problem dependent. So how do we find out? What we did was we initialized the crossover rate at 0.5. So we started the crossover rate CR at about 0.5. Then for every crossover operation, we generate a new crossover value using normal distribution, 0.5 mean value, standard deviation 0.1. So for every crossover operation, you randomly generate one value using this Gaussian distribution. If a particular problem requires higher crossover rate, what will happen is that when you generate using the normal distributions, the crossover values with 0.6, 0.65, 0.55, the higher crossover values will generate better solutions more frequently. And the lower crossover values like 0.4, 0.5, they will produce better solutions less frequently. So if you record the CR values giving you improved solution and then average them, your average will go up slowly. From 0.5, then it will become 0.55 or 0.6 and so on. And then in a few generations, it will go to 0.8, 9 and things like that, because that problem requires higher crossover rate. On the other hand, if your problem requires lower crossover rate, the CR value starting from 0.5 will just go down to 0.1, 0.2 and so on. So we did the adaptation for crossover rate as well. So this is the conference version, and this one was the journal version. And this particular crossover operator is very good as well. And the change they made was very simple. They did only small change to the original mutation operator. The whole equation is coming from the original mutation equation with only one change. Only this element is changed. In the original mutation operation, the original equation, this particular element was the best member in the population. So the original inventors of differential evolution proposed this mutation equation where they put this one as the best member in the current population. So instead of using the best member in the current population, this author suggested that instead of taking the best single one, you take one of the best top 10%, for example, or top 20%. Just take any one of them randomly. Only a simple variation, but the performance improved a lot. So this method is still used. Even now people use this particular method as well. The mutation operator, very popular nowadays also. In addition to changing the mutation rule, they also came up with crossover equations, and the scale factor adaptation equations. All these are based on success rates. I mentioned you the success rates, how we record them. So all of them are based on success rates. You record the past success rates and the values that are giving you better solutions. So the mutation, the crossover rate and the scale factor values that are giving you better solutions are recorded and then averaged, and the new values are generated. So all of these are based on performance feedback, but then they came up with for the crossover rate, they found out normal distribution is good. For the scale factor f, they found out Cauchy distribution was good. And for the mean, they said Lima mean is better for the scale factor. So they did, all these must have been done by doing lots of simulation. So they came up with all these rules by doing trial and error simulations. And the Jade version that you see here, this version was improved to become shade. So this is also one of the popular method, and the variation here is also very minor. So you make minor change and the performance improvements are consistent. So it's all done by heuristics, trial and error and simulations. Lots of simulations are going in. So the variation they introduced here is that in the Jade equations, over the last 10 or 20 generations, all successful values are averaged together collectively over generation. Over 20 generations, all promising values are averaged together into single average. So here you have single average for the crossover rate, single average for the scale factor, only one number. So what the shade authors suggested was that don't average over generation, but average for each generation separately. That's all. So the successful CR values, successful F values are averaged for each generation. And then they stored them. So they have a memory, historical memory of successful mean CR values and successful average F values. The averaging operation is done for one generation. In one generation, you average for the CR value, and the same generation you average for F and keep them separately. So how do you select for future generation? Out of the last 20 generation, you just pick any one of them randomly and then use those values to generate offspring going forward. So when they do that variation, they show that the values, CR values, F values are more distributed and the performance is improved. All done by empirical studies. So this is how you keep the historic memory for the successful CR values, these averages, successful scale factor values, averages, you keep them in the memory. And the new values are generated by normal distribution and Cauchy distribution. New values are generated to use in the future generations. The same authors also demonstrated the population size reduction was very good for the algorithm. So they used population size reduction here, and the linear population size reduction starting with a relatively large population initially and then going down to about 5 members eventually, improve the performance. So since I have only about 10 or 15 minutes, maybe I will say a few things about the constraint handling. So maybe I skip from here, move to constraint handling, but you can get the whole slides later on from the web page anyway. So maybe some other methods I will skip here. So these things you can see. This one also very effective, MPD, multi-population ensemble of mutation strategies. The performance is very good. This is also an adaptive method, ensemble methods, different implementations. And the performance evaluation is done slightly differently here. How each mutation is performing is evaluated using this equation, slightly different. So the performance evaluation, you can have several variations. So this is one particular method. So I will look at constraint handling method for about 10 minutes for you to give a little bit of introduction to the constraint handlings. So if you want to look at constraint handling related literature, you can look at these works anyway. So there are some literature here. So, the real world problems, all of them, many of them have constraints. If you look at real world problems, they have equality constraints, inequality constraints, and so on. So, how to work with them? Evolutionary algorithms, naturally they perform unconstrained search. Their search is unconstrained. So, you have to bring in another module, constraint handling module, with evolutionary algorithms. Most of the constraint handling methods are modular, they are independent, but you may have some integrated constraint handling methods also possible. Some constraint handling methods can be integrated with the evolution also. So, this is your constraint optimization problem, single objective case, numerical. This is your objective function. This is your inequality constraint. This is your equality constraints. There are a number of them, q of them, and here m minus q of them for the equality. When you do numerical works, optimization using numerical methods, the equal to 0 is usually impossible to satisfy with the floating numbers. With the floating numbers, you cannot have equal 0. So, all the equality constraints are converted to inequality with a tolerance. So, you have to specify a tolerance like 10 to the power minus 10. That means it is 0. You have to take it as a 0. So, with the tolerance, we convert them into inequality. So, all the constraints would become inequality constraints now. So, your problem formulation is something like this. Then the constraint handling methods. There are few constraint handling methods. The most popular one, the older one, is penalty functions. But the penalty function has a problem. You have to come up with a scale factor for the constraint violation to integrate with the objective value. So this method is old method, but not very effective if you look at the recent methods. So, there are recent methods that are much better than penalty functions. Another one is known as the superiority of feasible solutions. That means when you compare, yesterday also I mentioned all evolutionary algorithms require you to compare two solutions. You have to say which one is better. When you are given two solutions, you should be able to say which one is better. So, the superiority of feasible method, by the name of the method, it says feasible solution is superior than infeasible solution. So, that is the meaning of this method. So, when you compare two solutions, xi and xj, when both of them are infeasible, you look at the constraint violation. The solution with smaller constraint violation is better. When both solutions are feasible, you will say the solution with smaller objective value is better. When you do a minimization, objective value smaller is better. When one of them is feasible, other one is infeasible, you will say feasible one is always better. So, this is the superiority of feasible constraint handling method. And we also have self-adaptive penalty. Self-adaptive penalty method is also effective, not like the penalty-based constraint handling. This particular self-adaptive penalty method, there are lots of equations, but basically what it is doing is given here. The amount of penalty added is controlled by number of feasible solutions in the population. So, when you do constraint optimization, your first objective is to have a feasible solution. If you don't have a feasible solution, then you have no solution at all. That is the answer. So, your first objective is to find at least one or two feasible solutions. Then you can say this solution is feasible, satisfying all the constraints. So the amount of penalty added is controlled by number of the feasible solutions in the population. When the number of feasible solutions are very small, you add high penalty to infeasible solutions. So, infeasible solutions are highly penalized. When you have large number of feasible solutions, you want to improve the fitness value. So, you pay attention to the fitness. So you give low attention to constraint violation, but try to select solutions with high fitness. They may be violating the constraints. So your objective is changing from identifying some feasible solution first and then moving into improving the objective. So the feasibility satisfaction comes first and then improving the objective comes later. So that is a self adaptive penalty. So switch from feasible to optimality. First go for optimality, then try to minimize the objective first. So if I put the self adaptive penalty in here, so when you search for a solution, first the self adaptive penalty will first try to satisfy these conditions first. Find some solution that can satisfy these conditions. Once you have some solution satisfying the constraints, then go and reduce the objective value. So objective value comes later, first feasible solution. So that is the method of self adaptive penalty method. This is possibly the most effective method that we have now. It is a minor variation of superiority of feasible. So in the superiority of feasible method, all infeasible solutions are considered bad. All infeasible solutions are bad, where feasible solutions are better in the superiority of feasible solution method. Whereas this epsilon constraint handling method, it is considered the best method nowadays. Here we try to come up with the epsilon value for the constraint violation. So what it tells you is that if your constraint violation is smaller than epsilon, we are going to take this as a feasible solution in the initial stages. So you generate your initial population, say you generate 100 population members. Out of the 100 population members, usually we want to say 30% of them are satisfying the constraint, for example. So you go to 30% of the constraint violation and take the constraint violation at the 30% mark as the epsilon value. So what this method is telling you is, in the initial population, 30% of the population is satisfying the constraint up to the epsilon value violation. So these 30% of the population are regarded as feasible in the initial stages. So with this you will evolve the population. Once you evolve the population, the epsilon value will become smaller and smaller. And when you complete the evolution, the epsilon value will become 0. So the constraint violation, the tolerance of the constraint violation eventually will become 0. Initially it will be non-zero. So in the initial population, we are basically allowing small degree of constraint violation. Why is this useful? Because in the constraint optimization, most of the time the optimal solution is at the boundary. The optimal solution is usually at the equality boundary or inequality boundaries, at the boundary region. So if you do the superiority of feasible method, say this is your constraint boundary, this is infeasible, this is feasible, and this is your optimal solution. So what this epsilon constraint handling method is doing is, initially in the initial stages of evolution, it is going to allow your population to start from here, and it is going to say all these are feasible. Is that okay? So this will make it easier for the evolutionary algorithm. The evolutionary algorithm can generate solutions over all these places and evolve and go here. Is that okay? Whereas the superiority of feasible method, what it will do is, superiority of feasible method will say you cannot go here, you can only move to this point from this direction. Only from here you can go there. So that will make the search less effective, the superiority of feasible, as opposed to the epsilon constraint handling method. So anyway, the time is up. So I have given you some introduction to the constraint handling because you have real world problems with constraint handling. So you can make use of this. We also have an ensemble of constraint handling method where you can put multiple constraint handling methods together and make use of to solve a particular problem. And also in the recent time we proposed another method, skipping to the last method, variable reduction with the constraint handling. So in some cases when you solve real world problems, you may have equality constraints. When you have equality constraints, you may be able to reduce the variables. Reducing variables means you have capital D number of decision variables. Using the equality constraints, you can reduce these variables because most of the time equality constraints, inequality constraints are given by equations. So if you have equations, sometimes you will be able to make use of the equations to reduce the variables. So the problem space will become smaller and the constraints can be satisfied perfectly. So this work was published here, Applied Soft Computing. So the variability reduction is very simple. I just give you one example here. So this one, if you have a symbol, this is a very simple illustration. If you have x1 plus x2 equal to 2, it's an equality constraint, very simple toy example. So from this, can you get the value for x2? x2 will be 2 minus x1. So the x2 can, over here it can be replaced. So the two variables in the optimization will become single variable. But this one is not a general method because you have to look at the equality equation for every problem. You look at the problem. Sometimes these equations can become like exponential, sine, cosine. It can have all of them. When you have all those things, you may not be able to solve them like this. So if you are able to solve these equality equations, you can reduce the complexity of the problem. And for the inequality constraint also we extended this method, but that one will require a little bit of search. You have to do the search. When you realize that the inequality constraint is becoming active, you convert it to equality and then do the variable reduction. So inequality constraint is a bit difficult to apply this method. So we apply this method with real world problems. For the real world problems, when there are equality constraints, you apply this method, immediately you can show the improvement in the performance. And immediately you have a journal paper with, with the real world problems anyway. So with this I stop, it's almost 3 o'clock. So if you have any questions about differential evolution or all these constraint handlings, you can ask me now. So the exploitation population size can be about 5 or 10. That's what we found out. For any dimension, if you have about 5 to 10 members in the exploitation population, it is enough. But the splitting, exploration, exploitation, the exploration population, what is the best number? That is the problem, I think. But the exploitation size is about 5 to 10. That is enough. So anything more than that will become ineffective. The exploitation is more like you have almost found the global solution or good region. So your objective is to go here to this point. So if you put 20, 30 members here, you have to move each one of them closely, slowly here. So that means you are wasting function evaluations. you have to move one at a time, and if you are 30, 40, you have to move all of them. But basically, you don't need to have 30 members going to that point, is that right? What you need is about one member, but with differential evolution, you cannot evolve with one member. So minimum size for differential evolution is about 4 or 5 population size. So anything between 5 and 10, more than 5, less than 10 is good for most of the problems. Yeah.
And regardless of the dimension.
Yeah, that's right. That is when you reach here. When you reach here, that is what we tried like 10, 30, 50, 100. Up to 100 we have tried here in the competitions. So for all of them, they use about 5 to 10. I think just 5, I think. So they can do the work here. Yeah.
I'm Raj from Nanyang. I just want to ask about the success rate, the adaptive learning methodology. So let's say I'm trying to apply this DE for a single objective dynamic optimization problem. So is it still viable, possible to use this success rate? Because there can be some generational constraints between the changes. So is it still...
But it depends how frequently the objective function is changing. If you have some ideas, then you can learn it. But if when you see the objective function has changed, you may have to reinitialize, I think, the adaptation. If the characteristic of the problem has changed significantly, but in real world situation, the problem characteristics may not change, I think. But when you are solving synthetic problems, synthetic benchmark problems, the characteristics can change significantly. But real world problems, I think the properties of the problem will be similar and the changes will be minor, I think. Then you can continue to evolve, adapt, learn. For synthetic problem, you have to reinitialize.
Maybe thanks for your presentation. So for the ensemble methods, so one is used to explore the search space, and the other one is used to exploit the search space. So how do you combine the results from these two, some kind of conflicting methods?
I think I explained to you that, so you have larger population, exploration, and then you have a smaller population, exploitation. So this one is about 5 to 10 members. So you are going to evolve both of them. So we gave one function evaluation. Say this population will get one function evaluation. This population will get one function evaluation. But we had to select this R1, R2, R3 the best members in the population. So when we select R1, R2, R3 for exploration, we select only from this population. When you evolve these members here, we get R1, R2, R3, R4, all of them from here. When we evolve this population, we get R1, R2 from here. So the information is moving this way. So the information flow is only this way. So that one is the XR1, XR2, and things like that. So the information exchange is taking place always, every generation. Yeah. So what we are blocking is that information going from here to over there. So our objective is to maintain the diversity here, and we can allow this population to converge anytime. So it's a way of delaying premature convergence. So this PSO version is very popular anyway, it's becoming highly cited.